Explain the meaning of the following equation. Okay, so the way that you read this is the limit. Maybe I should write this down. The limit as x approaches one is 3. Okay, so that means that the values of fx are being made as close to 3 as we like by taking x sufficiently close to 1. Okay. So generally, so let me take a look at the graph right here. So here's 1, and then 3 would be on the y-axis. Okay, so 1 would be on the x-axis, 3 would be on the y-axis. And as your function is coming along, as you come this way or you come this way, it's going to approach 3. Okay, now the limit does not, it doesn't matter what the value is at when x is 1, or even if it exists, that doesn't matter. It's what's happening as you're approaching 1, what's happening. That's what matters. So right, in the second part, is it possible for this statement to be true and yet f of 1 equals 9? So f of 1, let's say that's, I don't have enough space, but let's just say this is 9 right there. So this would be a situation where the limit is 3, but the value is 9. And that would be this one here. Yes, the graph could have a hole at that value. The hole, meaning a hole right here. So when it talks about hole, it means this right here, a hole right there, and be defined such that f of 1 is 9. So here's actually where the value is. Okay, so that's a little bit of terminology there. Oh dear, what do I do? Okay. Okay, so let's look at the number 2. Explain what it means to this and this. Okay, so this is as x approaches 1 from the left. Okay, so the minus sign means left. And then the plus sign here means from the right. Okay, so as you approach 1 from the left, you're going to 3. As you approach 1 from the right, you're going to 9. So this is going to look somewhat like this. So this is 1 right here, and here's 3, here's 9. So what it's saying is, as you're coming from the left, you're going towards 3. So you're coming this way, you're going to 3. As you're coming in from the right, you're going towards 9. Okay? You're going to 9. Okay. Wait. So it'd be this last one right here would be the correct one. As you're coming from the left, it's going to 3. As you're going to 1 from the right, it's going to 9. So that would be a picture of what it looks like. Okay, in this situation, is it possible that the overall limit exists? And the answer there is no. Okay, so for this to exist, okay, so for this to exist, you have to have that the limit as you're going from the left has to be equal to the limit as you're coming in from the right. And also, if these two are, if these are equal, if these two limits are equal, coming from the left and coming from the right, they're the same, then the overall, then this will exist. So this right here is also called necessary. So this is necessary for this to exist, and sufficient. So that means that if this is true, then this exists. Okay? Or if this exists, then this is going to be true. Okay, let's go to the next exercise. Number 3, explain the meaning of each. Okay, now we're talking about limits being infinity. And the key here is infinity is not really a number. So the phrase here is arbitrarily large. So values get arbitrarily large. Okay, so as you approach, see, this one is always the approach. The values of f can be made arbitrarily large by taking x sufficiently close to, but not equal to -1. That would be this one right here. And then the second one would be this right here. This is as you're approaching 3 from the right. The values can be made negative with arbitrarily large absolute value by taking x sufficiently close to, but not close to, but greater than 3. So greater than 3 would also be to the right. Okay. So this is from the right. So when you're, in other words, so let me see. So this first one, that is going to look something like this. If this is negative, this is -1 right here. Then one way to do that is to have an asymptote, and that would be like that. And this one's coming up this way. Okay, and a function that might do such a thing would be an example of a function. It's not the only function. There could be, literally infinite many functions that can do this. But one function that would do it would be 1 over x plus 1 squared. Okay, that would do that. And in this second part, here as you're approaching 3 from the right, you're going off to infinity. Wait, no. Negative infinity. What am I thinking? So you're going down to negative infinity like that. Okay, now one such function that could behave this way is -1 over x plus 3. As you come in from the right, this is becoming really, really small, but it's positive because x is greater than 3, right? So you take something greater than 3, I'm sorry. I'm sorry. This should be -3. Sorry about that. So you take something greater than 3, and you subtract 3 from it, you're going to have a positive number. Okay, now as you approach 3, that positive number gets smaller and smaller and smaller. So you're taking 1, you're dividing it by smaller and smaller and smaller numbers. That's going to blow up to infinity as you approach 3. Okay, but then it's negative. So then you have this negative here, so it's going to go down that way. And this function right here actually does this as well. It'll come up like that. So as you approach from the left, with this function, as you approach from the left, it actually goes to positive infinity as you approach from the left. As you approach 3 from the right, it goes to negative infinity. So that's an example there. Here I got around that and made them both do the same thing by squaring this. So everything's positive. Okay, let's look at the next one. So here, we don't have a formula for the for this, but we just have a picture of the graph. Okay, and we're supposed to answer all these questions here. Okay, so let's go ahead with the first one. The limit of x approaches -3 from the left. So here's -3 right here. It's this right here. As you come in from the left, this is going to 4. That's going to be 4. As you come into the right, that's also going to 4. Overall, it's going to be 4. Because going from the left and the right is the same thing. Okay, so those are going to be 4. Now, h of -3, there's a hole in the graph there, and there's no, it doesn't say where it's defined. So like right here, there's a hole, but it's defined right here, because you see a darkened circle right there. You don't see any darkened circle here, so this one does not exist. So if it doesn't exist, then you enter D and E. Okay, now let's look at the point 0. Okay, as you come in from the left, it's going to 1. So here's 0. That's going to 1. That's 1 right there. As you come in to the right, you're going to -1. As you come in from the right, you're coming down here, and that's going to -1. Overall, this goes to 1, that goes to -1. Well, those are not the same. So this one is, this one does not exist. And we discussed this, but h of 0 is right here. It's at 1. It's 1. Okay, and then we also we have the number 2, which is right here. And the limit as x approaches 2. Okay, think about what it is, okay? Before I give the answer. Think about those two. What do you think it is? Okay, the answer is 2. Because you're right here at 2. So that's going to be 2. And then this one does not exist because there's an open circle, there's a hole right there, but there's no solid circle anywhere. Okay, and let's do the last one, that's 5. So 5 is right here. Okay, so as you come in from the right, you're coming like here, and you're going towards this point right here, which is at 3. Okay, so that's going to be 3. Now, as you come in from the left, they're having to do this, it's kind of jumping up and down right here is what they're trying to graph. So it's doing this like this. And so this one is not going to exist. Okay, now a function, let me just give you an example of a function that does this sort of thing. It would be something like sine. The classic example would be sine of 1 over x. Okay, so the limit as x goes to 0 from the right or from the left does not exist. Okay, because what happens is as x goes to 0, 1 over x becomes arbitrarily large. It just starts blowing up to infinity. And you know that the sign oscillates between -1 and 1. So now if you wanted to get an effect like this, then you could have it be sine of 1 over x minus 5 3 plus that. You could have it do that, and this would look something like that right here for that part. And then just define it to be different over here. Piecewise define function, and the first thing is to sketch the graph. And then the second one is to determine the values of a for which the limit does not exist. Okay, so the way that I like to do this is we'll go ahead and draw the, let's do it right here. We'll draw the coordinate axes. And when x is less than -1, it's 1 plus x. Okay, so I'm going to put at -1, I'm going to mark that off. And then this one right here, I guess 1 plus x is the same as x plus 1, right? So that's this right here. That's the equation of a line. And it's got the y-intercept at 1, and then the slope is 1. So it's going to be like that. However, it's not defined. So this at -1, it's not defined to the right of -1. So that means that it's going to be going down like that. Okay. It's going to go like that. It's got slope 1. So if we continue this out, it would be a line of slope 1, and the y-intercept would be 1 right there. So slope 1, y-intercept 1. Okay, the second one is a parabola, but it's only between -1 and 1. So if only go from here to 1. Okay, now it's including -1. But the parabola is going to go like this. But over here, it's not not going to be including a 1. So that's like that. Okay. And then the third one, that middle part's going to be that. And then the third one is, if we look at it this way, -x plus 2, that is a line, and the y-intercept is up here at 2. Okay, and the slope is -1, so it's going to come down like this. It's actually going to go through here. Actually, it's going to start right here because it only goes from 1 on over. So it starts right there and goes down like that. Okay, so that's what the graph is going to look like. And that is looks like the first one, the first graph on your homework. Okay, and then the second part is does the limit does not exist. And it's not going to exist here because as you come in this way, you're going to 0. And as you're coming from the right, you're going to 1. So -1 is where it doesn't exist. So when it's asking the values of a, okay, so right here, a equals -1. So that limit doesn't exist because the limit as x approaches -1 from the left of f of x is 0. So as you're coming from the left is 0. And the limit as you go from the right is going to be 1. So as you come from the right, it goes to 1. Okay, and then these are not equal. Those are not equal. 0 is not equal to 1. So that doesn't exist. Now here, interestingly, so when you have this kind of functions like this, a lot of times is you look at where at these boundary points, so -1 and 1 are the boundary points, where it changes from being one formula to another. And those are good candidates for when the limit doesn't exist. But this one right here, they both match up. So they both go to 1. So that limit does exist, even though it's kind of a spiky there. The limit still does exist right there. Okay. So let's move on to the next exercise. Again, if you have any questions, just ask anytime, okay? So number 6, you want a graph where the limit as x approaches 3 from the right is 4. So I can kind of do a little bit of sketch of what this is going to look like. So this first piece, as you're going from 3, if you're going to 3 from the right, you want to be 4. So you want to go towards 4, something like that. Or it could come down like that, but it's going towards 4. Okay. And the second part, as you're going from the left, you want to go to 2. So here, it's going to be coming to 2, like right there somehow, as you go there. And we can look and see which ones do that. So this one goes to 4, and that one goes to 2. This one doesn't go to 2 here, so you got to be going. You got to somehow to go to 2. So that's going to be wrong. And that answer is not going to be it. This one's okay. So that's okay. That's that, and that's that. Let's look at the other one. So this one is as you're going to from the right. Wait, what the heck? This one's neither. This one doesn't satisfy either. Okay, and then this one, let's see here. As you're going from the as you're going from the right, you want to be 4, but this is going to 2, so that's not right. Okay, so that's okay. So looking at the first 2 conditions, then the only one that satisfies so far is this one. Okay, so let's look at this next one. As you go to -1, you want to be 2. 2. Okay, this is the case. As you're coming in right here, you're fine. And then f of 3 needs to be 3. F of 3 is, here's 3. Yeah, that's fine. F of 3 is 3, and f of -1 is 1, and that's fine too. F of -1 is 1, so that's fine. So the first one is going to be the answer to that. Okay, that's kind of fun. So let's do. Of course, that's not the only function that can do that. We could, like this one I'm starting to construct here looks very different, right? I could make that work. Okay. So let's go to the next one. This is number 7. You're looking at the limit of a difference quotient. Now, these difference quotients are very important because what it represents is what this one represents. Let's just say this, like if you have this function right here, x cubed. Okay, now I got this from looking at this quantity right here. And then saying, okay, 2 plus h is cubed, right? 2 plus h is cubed. Plus, we know that, so essentially, if you have this function and you're looking at, what this represents is the slope at 2 comma f of 2, which is 2, 8. So this graph goes through the point 2, 8, right? This is going to represent that slope. Okay. It is the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Okay, so you can see that f of 2, okay, so this function here, if you put a 2 in here, you get 8, right? So that's this. And you're subtracting that. And then f of 2 plus h, if you put a 2 plus h in here, you get 2 plus h cubed. So that's that part. And then you have this, and then they're minus, and then you have the h. So that's what that is. And that represents the slope at that point of the graph. Okay, so if I illustrate that, okay, this is x cubed. So it's going to go like this. Come down like that. And at 2, we're up here at 8. And this is going to be the slope of that tangent line. The tangent line that goes through that point that's tangent to the curve. That has the same slope of the curve. Okay. So that's what that represents. But now let's do, and so this is probably the first, one of the main key points of calculus. Okay, so you're looking for this slope of this tangent line. It also represents if you're looking at applications, it can represent things like instantaneous velocity, which we talked about last time as well. Okay, so this one right here, I'm going to do using Excel again. So I'm gonna, so just keep in mind, this is what we're after right here. And so what we're doing is we're actually taking this expression here and we're plugging in different values of h. Okay. Just a second. Let me think. Okay, so I think I've confused everybody because I should have labeled this like G or something. Okay, because f of h, what they want it to be is this right here. They want it to be that, okay? So we'll remember that right there, and we'll plug in these different values for h. And then we'll do that in Excel. So let's, I'll cut out right here, go over to Excel. So I have a blank worksheet, okay? And I'm going to like make some room. So now this is going to be my h right here, and this next column will be my f of h. And the values that we have was 0.5, 0.1, 0.01, 0.001, 0.0001, and then we had negative 0.5, negative 0.1, negative 0.01, negative 0.001, and negative 0.0001. Okay. And then, okay, so the expression right here is there's 2 plus h, but h is a2, okay, to the third power minus 8. That's the numerator. Okay, so I have parentheses around the numerator, and I have parentheses around this 2 plus h part. But it's a2, and now you lead it off with an equal sign, because that's telling you that's going to be a number. And then you're dividing by this a2 right here. Okay, so that gives me that. And then once again, I can double click here, or I can just drag that corner down. Okay, and that gives me, this gives me effectively all of the values. Okay, so here's all the values right there. And they're supposed to round them all off to 4 decimal places. Okay, so once again, Excel just gave me all the values. I'm going to copy them over onto the, wait, hold on. I'll copy them over. I'll copy them over onto the document right here. So, and rounding off at the same time. Okay, so I'm rounding off at the same time. So 15.25, 12.61, 12.0601, 12.006. Wait, 6 decimal places. 001, and then 12.6, no, 0, 0, 0, 6, so 6 decimal places, and then 9.25, 11.41, 11.9401, 11.994001, and then 11.9994. Okay, so those are the different values from the Excel spreadsheet, rounded off to 6 decimal places. Now, the idea is you're trying to see what happens as h goes to 0. So here you have the h is 0.5 here, and it goes down to 0.1, 0.00, 0.0001. So this is really small. This is also really small, but negative. And so these appear to be going, this is really close to 12. That's really close to 12. This is greater than 12. That's less than 12. And so the answer to this, the second part would be 12. It looks like they're going to 12. Okay, and I put the Excel spreadsheet up onto Canvas, by the way, in the files. Okay, so let's go on to, any questions so far about anything? Okay, let's go on to the next part, number 8. So here, you're just trying to figure out particular limits. Okay, so this first one, these are infinite limits. So the answer is either going to be infinity or negative infinity. But let's not guess. Okay, let's do this in an organized way. Okay, so the graph of the logarithm is like this. At 1, it's going to go through 0, and then it's going to come up like that, right? And it has a vertical asymptote on the y-axis. Vertical asymptote on the y-axis. Okay. But this is y equals natural log of x. But what we have here is something different. We've got natural log of x squared minus 1. But let's just like use this for reference as to what's happening. Okay, so as x goes to 1 from the right, what's happening there? So so maybe you can think of it like this. Think of like 1.5, and then 1.1, and then 1.01, and then 1.001, and so on. You know, what is happening as we go through these kind of values? Okay. So if x is 1.5, that's going to be 1.5 squared. I forget what that is. But it's 1.1, 1.1 squared. So these are going to get closer to 1 right here. But they're always going to be greater than 1. So you have something. So basically, you have something that's close to 1, but greater than 1, minus 1. Okay? And that's going to give you a small positive number. Now over here, small positive number would be like right here. These would be small positive numbers would be right there. And so what's happening is that as these numbers are getting smaller, positive numbers are getting smaller, your graph is going to go, their values on this graph are going to get small, you're going to go down, 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 down. Okay, so that means that this goes to negative infinity. Okay, and that's going to be the answer. Okay, let's look at the second one. This limit right here. Now, it looks like we could get some canceling going on here. So the numerator factors into x times x minus 2, and the denominator factors into x minus 2 times x minus 2. Okay, and so these are going to cancel out or reduce to 1. Okay, and which, when you do this kind of thing, it doesn't affect the limit ever. You know, even though you're going to the point 2, it doesn't matter. Because this function, this is not defined at 2 anyways. Okay, so you have x over x minus 2. Okay, so now as you're approaching 2 from the left, this minus means you're approaching from the left. Okay, so from the left. So you're going through numbers, you think of numbers that are close to 2, but less than 2. Okay, so like 1.5, 1.9, 1.99. Okay, things like that, because that's what you should be thinking right there. And maybe like you can't get to sleep tonight, you just count you count the nines on the end there, 9, 9, and then you go another 9, 9, 9, 9. Eventually you're gonna like a whole bunch of nines. Eventually you'll fall asleep if you try to do that. Okay, so the numerator is going to be close to 2, right? So that's going to be positive in the numerator. But the denominator, when you have numbers that are less than 2, and you subtract 2 from it, you're going to get negative. Okay, so you have like a number that is going to be close to 2. And then this number is going to be close to 0. Okay, because if you take 1.99 and subtract 2 from it, you're going to get negative 0.01. Okay, and if you take this one and subtract 2 from it, you're going to get negative 0.0000, a whole bunch of zeros and then a 1. Okay, and if you take 2 and divide by that, that's going to be a huge number. Okay, so like if you take 2 divided by 0.0001, that's actually like 20,000. Okay, but if you have like more zeros, then it's more zeros here, bigger. Okay, so those are the kind of things you think about. Okay, but this is negative, so again, what's going to happen is you're going to get, it's going to be negative infinity again. Whoa, that's weird, because 2 negative infinities in a row.